You're welcome back. All right, so here in this video we are going to be talking about the reflection of light. All right, so let's start by definition. Okay, what is reflection? Reflection is the bouncing back of light as it actually encounters an obstacle. All right, but before we actually describe reflection, before we go into details, okay, describing how light actually undergoes reflection, now we need to actually study some basic concepts, all right, that surrounds light. Already know that light, okay, is an energy or a wave. Okay, so light is the type of wave, okay, that stimulates the sensation of vision. All right, so which simply means that there is no vision without light. In fact, okay, for you to be able to see an object, what you see, okay, anytime you look at an object is the image of the object, okay, that is formed at your retina. Now the eye has the part known as the retina. So it is the light rays that reflect from an object that forms the image at the retina, okay, that actually make you to see that object clearly. So without light, in the absence of light, vision is not possible. So light is actually a wave that stimulates the sensation of vision. Okay. Now, as I've already said, okay, we're going to be looking at some basic terms before we now go into the reflection of light. All right, so now what are these basic terms that we need to learn? Okay, one basic term we need to know before we go into this reflection of light is, okay, ray of light. You need to understand what ray of light entails. Okay, ray of light. Now a ray of light, okay, is actually a line that represents a tiny source of light coming from a very tiny source like that of a pointer. So we just use a single line to represent a ray of light, okay, and this light is actually coming from a very tiny source. Now if the light that's okay if the light is coming from a very large source, then we don't just use a ray of light. Okay, we don't just use one line. Rather, we represent that by what is known as the beam of light. Okay, beam of light is made up of many rays of light. So, and of course, is used to represent light coming from a very large source, like a satellite. Okay, so and now this beam of light can be of different type. It can be parallel beam, as you can see here. What I'm having here is a parallel beam, probably coming from a searchlight. Okay, so this is parallel beam of light. Okay, or it can also be what is can be convergent beam. Convergence simply means that they actually come from somewhere to meet. They meet at a particular point. They converge at a point. Okay, so convergent beam. So when you see this, such beam is said to be convergent because they meet at a point. Convergent beam. Then the other is what is now known as divergent. Divergent, okay, move away from each other. The rays move away from each other. Divergent beam of light. So as you can see, the arrow is actually pointing away from a source. This is the source. Okay, so once you see this, it means that this beam is actually divergent. So I hope that is well understood. Okay, now let's actually proceed. So if that being the case, now we could actually look at some other details. Here we are going to be talking about the types of reflection. Okay, two types of reflection. Now refraction, if refraction occur, okay, that reflection can either set to be a regular reflection, or the reflection is said to be diffused. Okay, so what is the difference between these two? All right, now a regular reflection actually occurs at a smooth surface. When the reflection actually occurs at a smooth surface, then it's said to be regular reflection. Now, for example, this is actually a smooth surface. Okay, so reflection of light at a smooth surface is regular reflection. Now, of course, you know that once that reflection occurs, we use this. Let's use this is the incidence. Okay, incidence beam of light. Now, because the surface is actually smooth, okay, please pardon me, as the incidence ray hits the surface, it will reflect. Okay, and if it reflects, the incidence ray are parallel. Then because the surface is smooth, as the incident reflects, it will also produce a parallel rays of light. Okay, so that simply means that the reflected ray does not cross each other. Okay, so since the incidence is parallel, the reflected ray does not cross each other. So this is regular reflection. But what is different from a diffused reflection? Okay, now diffused reflection occurs in a rough surface. Okay, for example, let's look at a surface that is rough. So in a case like that, the parallel beam of light, okay, that hits the surface, after it actually reflects, because the surface is rough, so it happens that the reflected ray will cross each other. Okay, so the reflected ray will definitely cross each other. Why? Because the surface is rough. So this happens in a rough surface, and this actually happens in a smooth surface. Please pardon me. Happens in a smooth surface. All right, so I hope that is well understood. Now I'll clean up. Let's look at okay, the terms that is used to describe reflection that actually happens in a smooth surface. Right, okay, so I have a smooth surface, and of course the part I'm actually polishing, okay, is not the reflected surface, is behind the reflecting surface. The up part is the reflecting surface. Now for me to be able to study, okay, the different parameters of reflection in a surface, the very first thing I'm gonna draw is a line that is perpendicular to that surface. That is the normal. Okay, so having drawn the normal, and of course this line normal, okay, is perpendicular to the surface. Now I can now draw a line known as the incidence ray. So I use this line to represent the incidence ray. And of course, after it's been incidented, then it will reflect. I'll use this other line to represent the reflected. Okay, so now, of course, this is the incidence. And this is the reflected ray. Now, why the line, okay? The perpendicular line is known as the normal, okay? This is the normal. Now, the angle that the incidence ray make with the normal is what is known as angle of incidence. So I use I degree to represent that. And the angle that the reflected ray, okay, please pardon me, reflected ray makes with the normal, I use R0 to represent that. Okay, so which simply means that I degrees, okay, from the loss of reflection, we know that, okay, already. Let me first write I degrees is the angle. I call this is the angle of incidence. So that is the angle the incidence actually makes with the normal. Please take note of that. Then of course R degrees is the angle of reflection. Now according to the law of reflection, okay, law of reflection, now we are meant to understand that the angle of incidence I degrees is always equal to the angle of reflection. Please take note of that. So whatever angle of incidence we have is always equal to the angle of reflection. It's very important for you to know. Now, so, but apart from this, there's another angle that I can actually express. The angle that, there's another angle, I'll call it theta, okay? This is the angle that is either the incidence or, okay, or the reflected ray makes with the surface, the reflecting surface, okay? This angle theta is what we refer to as a glancing angle. So invariably now, okay, remember the surface and the normal is actually perpendicular to each other, right? So let's look at a situation where you are being given the glancing angle, okay? The glancing angle is the angle between either the reflected ray, or even the incidence ray with the surface, okay? So invariably now, if I want to actually get my angle of reflection from the glancing angle theta, or even the angle of incidence, okay, it is always going to be 90 minus angle of incidence. So a situation where you are being given such a surface where glancing angle is given as 45 degrees, okay, and you're being asked to find the angle of reflection, okay. So of course the angle of reflection, which is also equal to the angle of incidence, is just going to be equal to 90 minus 45, and that case will give us 45 degrees. Okay, so I hope that is well understood. Now, apart from the glancing angle, angle of incidence, and angle of reflection, there's another angle too we need to also measure, okay, on the reflecting surface. That angle is called the angle of deviation, okay. The angle of deviation is the angle between the initial direction of the ray and the final direction. Let me draw my normal. Okay, so of course you know that the initial direction of the ray is that of the incidence. The initial direction of the ray is that of the incidence. Have this. The final direction of the ray is that of the reflection. So this angle all the way, let me use another color, between the incidence and that of the reflected ray, okay, is what we have as the angle of deviation. These degrees, angle of deviation, okay, the angle between the initial and the final direction of the ray. So the question is, how will I be able to calculate this angle of deviation? Of course, you know already that this is angle of incidence, right? And this is, let me use another color, angle of reflection. All this angle, incidence, reflection, and deviation, they actually form a straight line, okay? They are all angle in a straight line, as you can see here. So invariably now, you know very well that an angle in a straight line, the sum of the angle in a straight line is equal to 180 degrees. That's I degrees plus R degrees plus even D degrees, okay, is equal to 180. So that way you can be able to get any particular parameter you're looking for. Okay, let's look at a typical example. Let's look at a situation where an engineer was asked to deviate a ray of light, okay, to 120 degrees. Now the question is, what will be the angle of incidence? What is the angle of incidence for such deviation to occur? Okay, so question mark. So apply the formula. Solution. Angle of incidence is what I'm looking for, right? Don't forget that angle of reflection is also equal to angle of incidence. Don't forget that. I can still represent that by I0, okay, then plus the deviation. Angle of deviation, everything is equal to 180. I plus I will give me 2I, so I'm having 2I, okay, that we're going to be equal to 180, of course, minus the deviation. The deviation that was given is 120 degrees. So now that simply means that my angle of incidence now is going to be equal to 180 degrees minus 120. That gives me 60. Don't forget I have to divide by 2. 60 divided by 2. Okay, so that means my angle of incidence from angle of deviation is going to be 30 degrees. So I hope that is well understood. All right. So take note of that. Now, I told you that the whole idea of reflection, okay, and of course light, is to produce image. Every image that you see is due to the reflection of the light coming from that object that forms the image at the retina. Okay, now there are some actually devices that produce a red, okay, clear image of an object, and that is the device we are going to study. Okay, those devices actually produce those image through reflection. So we're going to start studying reflection in a plane mirror. Okay, reflection of light in a plane mirror. Okay, so let's start. So what's a plane mirror, and of course how does it look like? Now a plane mirror is actually a piece of glass, okay, that is actually polished at one side to create a reflecting surface that produces an erect, okay, and at the same time virtual image of the object placed in front of it. Okay, of course I'll tell you what virtual simply means. Now let me tell you how plane mirror forms image by reflection. Let's say you have an object, Okay, this object that's placed in front of a mirror. Okay, so if you want to see this object through this mirror, it's due to the fact that the rays of light from this object, okay, as it reaches the mirror, okay, it doesn't pass through the mirror because the mirror is already an opaque body. Okay, the only thing it does is that it will only reflect. So this ray of light reaches this mirror, it reflects. So of course, you know, this is the incidence and this is the reflected ray. The same thing, another ray coming from this side hits the mirror. Okay, it will also reflect. Now of course, you know that this reflection actually enters the eye of the observer. Okay, let's say this is the observer that is actually looking. Okay, this is the observer looking. So this ray of light actually enters into the eye of the observer. So that if this observer is actually looking at this object in the mirror, okay, what the observer will see will be traced, the image will be formed only if I trace this reflected ray, okay, virtually behind the mirror. And you know that ray of light doesn't pass through an opaque object, okay, but that's why I see we're using a dotted line to actually represent that. Now the point where this ray intersects, that is where the image is being formed, and that is why the image that is formed by a plane mirror is said to be a virtual image. It's not real. Okay, so when you look at your image in a plane mirror, it is virtual because it seems as if your image is formed, is behind the mirror. But if you go behind the mirror, you won't see yourself, but you look at yourself in the mirror, it seems as if your image is behind the mirror. That's why it's called virtual. Right? It is not cast on the mirror. So invariably, now the characteristics, let's look at the characteristics of the image formed by a plane mirror. Okay, so one of the characteristics of the image formed by a plane mirror is what I've just mentioned, that it is actually virtual. Then the second characteristics of the image formed by plane mirror is laterally inverted. Now, what I mean by lateral inversion, lateral inversion is just horizontal, okay, flipping of an object. The same way we have upside down, okay. So lateral inversion is more like right side left. Let's say you have an object, okay. Let me show you how lateral inversion actually works, okay. Okay, so I'm going to shed perhaps one side of this object, okay. Okay, so let's say this is the left hand side. So if this object should actually be seen through a mirror, see what happens. It will rotate, okay, horizontally. So that's what I mean by lateral inversion. So invariably now, if you should write the word Victor in front of and place it in front of the mirror, the image you will see will not go, okay, the same way. It will go like this. So that simply means that, okay, if you stand in front of a mirror, your left hand side ceases to be your right hand, okay, and your right hand is becomes your left hand. That's lateral inversion. So I hope that is well understood. So that is how a plane mirror forms image. Then apart from this characteristic, apart from it being laterally inverted, another, okay, characteristics of image formed by plane mirror is the same distance. The image is same distance with the object. Same distance from the mirror. Okay, with the object. So that simply means that if the object happens to be, let's say, 20 cm from this mirror, then the image will also be 20 cm. Even if you shift the object, okay, the image will also be adjusted. Okay, so it's same distance, so please take note of that. All right, so I hope that is well understood. So now we are going to extend it now to reflection in a curved mirror. Okay, so we are looking at now reflection in a curved mirror. Okay, so let's now, what's a curved mirror and how is that constructed? Now, a curved mirror is a mirror whose reflecting surface is actually curved. Okay, and how is it constructed? A curved mirror is simply made from part of a sphere. Let's say this is a sphere. Okay, you actually cut out just part of this sphere, the ground. Okay, then you now polish one side and coat the other side to create a reflecting surface. Then that way you've actually created a curved mirror. So this is actually a curved mirror. Now, if you place an object in front of the reflecting surface, this is a reflecting surface, then your image will be formed. Okay. So now, curved mirror is of two types. Let's look at the types. We have what we call the concave, okay, or converging mirror. So it's either is concave or converging. I will tell you why it's called concave or converging. Then the second is convex or a diverging mirror. All right, so now let's starting with the very first one, concave. Okay, now this mirror I've actually constructed now. This mirror here is actually concave or converging. Now, why is it called concave or converging? I'll tell you why. Let me bring it here. All right, now it's called concave. Okay, first it's called concave. Why? Because the reflecting surface, as you can see, okay, this side, this left hand side is the reflecting surface, is curved inward. So the reflecting surface is curved inward, as you can see here, okay, curved inward. But it's called convergent because parallel rays of light that incident on the mirror will reflect. As they reflect, they will converge at a particular point, known as the principal focus. Now I'm drawing a line, okay, through the center of this mirror. This line is called the principal axis. I don't use this line to represent any ray of light, so the line through the center of the mirror is not for rays. Okay, so we'll call that line principal axis. All right, then any other line apart from the one that's going through the center, we call the parallel axis, and we use it to represent the rays of light. Okay, so this is the parallel axis, 1, 2. Okay, 1, 2. So of course these are parallel rays of light. All this represent parallel rays of light that incidents on the mirror. Now, as these rays incidents on the mirror, they will definitely reflect. But one thing about their reflection is that as they reflect, all of them will converge at a particular point, at a common point, okay, known as the principal focus. So that is why a concave mirror is also known as a converging mirror, okay, because it converges the ray of light at a common point, which of course is the principal focus, F. All right, so now we are going to be looking at the terms, okay, that is used to illustrate a curved mirror. So these are the terms I'm going to use this diagram to illustrate the term. First, I have told you about the line that passes through the center of the mirror, okay. That line, we call it the principal axis, okay. Of course, it's principal axis. Why? Because the key point of the mirror is actually being represented on the principal axis. What are the key points? The very first key point of the mirror is the center of the mirror. Okay, the center of the mirror is the pole of the mirror. I use P to represent that. All right, then we now have this point I've already represented, the point where all the parallel rays of light, after they have reflected, converge. Okay, that is the point known as the principal focus. So the P is the center of the mirror, which are called is the pole of the mirror, while the F is the point where all rays of light meet. Okay, so which are called this is called the principal focus. The principal focus of the mirror. Okay, now when you go go from the pole to the principal focus and you go another distance 2 times from the pole, the same when you go principal focus, okay, 2 times, you have another point, okay, still along the parallel axis. Okay, the point I call it C. I'll use it to represent it. Capital letter C. So capital letter C is actually 2 times the distance of the principal focus from the pole, right? We call that the center of curvature of the mirror. Center of curvature. Now the center of curvature is actually the center of that particular sphere where this mirror was actually made from. Okay, I hope that is well understood. Okay, all right, so now let's proceed. Okay, so principal focus, center of curvature. Okay, now let's look at distance. The distance between the pole and of course the principal focus of every mirror is what is known as the focal length of the mirror. Focal length. So the distance between the pole and the principal focus is the focal length, and I'm using small letter f to represent that. Okay, so the distance now between the pole and the center of curvature is what is known as the radius of curvature. Okay, I'm using small letter c to represent it. Now know that the radius of curvature is always 2 times the focal length. Please take note of that. Radius of curvature is always 2 times the focal length. Okay, so basically, and all these rays of rays of light, okay, we'll call this the parallel axis, or this line that is used to represent rays of light, okay, call them parallel axis. They are used to represent parallel rays of light that is incident on the mirror. Okay, so now having known the basic so let's actually talk about this is concave, okay, or converging mirror. Now how does a convex mirror look like? Now convex mirror, why is it called convex or converging mirror? Convex or diverging, please pardon me. Okay, okay, so as the name implies, this time around for a convex mirror the reflecting surface is actually curved outward. So you see, okay, this is what you have. Okay, please pardon my diagram, let me draw that well. All right, so this is what you have. So this of course is this is the reflecting surface. All right, and it's curved outward. but it's actually called diverging mirror. Okay, of course, for me to explain that, first of all, let me draw my principal axis. Okay, principal axis. Then, so in the case of okay, now in the case of diverging mirror, okay, the parallel rays of light that incident on the mirror, okay, yes, they will reflect, but after the reflection they don't converge, but rather they will move away from each other. Okay, they diverge. So what you have in terms of a diverging mirror is, after this ray hits the mirror, they reflect. After they reflect, they will move away from each other. They will diverge. Okay, so that is why it's called converse or a diverging mirror. Okay, I hope that is well understood. So now we are going to look at the characteristics of the image formed by a curved mirror. Now, unlike a plane mirror that has, okay, the same characteristics of image it forms, irrespective of the position of the object, but a curved mirror will have different characteristics of image, okay, depending on the position of the object. That is why, for us to understand the type of image, okay, that a curved mirror will actually form, we need to, okay, understand mirror equation. I will introduce mirror equation. Mirror equation is equation that actually connects the focal length of a mirror, okay, the object distance, and of course the image distance together, because all those things they actually work hand in hand. Okay, focal length of the mirror affects the image, the nature of the image, and of course the object distance also affect the nature of the image. So that means invariably now have that this is the formula: 1 all over f mirror equation is equal to 1 all over u, then plus 1 all over v. Okay, this is the form, this mirror equation or mirror formula. Okay, the u, the f here, of course, represent the focal length of the mirror. So every mirror has its focal length. The u represent the object distance. Okay, so why the v actually represent the image distance? So invariably now, the image distance now depend on the object distance and focal length. Why? Because if I want to get the image distance, it all depends on the position of the object and of course the focal length of the mirror. Okay, so due to that, you can simply say that a plane mirror can have the following characteristics. Okay, look at the characteristics. It's either its image, okay, let me bring that down. It's either the image it forms is real, or it can be virtual, depending on the object. Number two, it's either is erect or it is inverted, still depending on the position of the object if in front of the mirror. Okay, it can also be magnified, that is bigger than the object, right? The image can be magnified bigger than the object, or the image can be less than the object, and that is diminished. Okay, diminished. All right, let's flow. Okay, with what I have here, real, virtual, erect, inverted, magnified, or diminished, all this can be the nature of the image depending on the position of the object. Now, what you should understand, okay, this formula that we have here, let me actually bring this down, okay? This formula that we have here, okay, is plus here because the image is actually real. Now, a situation where the image, okay, is virtual, a virtual image will always have negative sign. So the formula now becomes for virtual image, okay? So a situation where v is for virtual image, then the formula becomes 1 all over u, then minus 1 all over v. Okay, so this is really very important. It's very important for you to know so that you know when you apply minus or plus. Okay, now the question, how do you know if the image is virtual? Now let's now go to, okay, the ray diagram proper. So now the nature of the image, as already we've said that already, okay, depend on the position of the object with respect to the principal focus. Now let's look at a situation where the object is placed before the principal focus. That is, the object distance is less than the principal focus. Okay, let's draw the ray diagram of that. Okay, so a ray diagram is actually used to show how image is formed, okay, in a mirror. So we use ray diagram to represent that. Of course, you know very well that this actually forms my principal axis. Okay, so having gotten my principal axis, now I need to actually draw my, of course, the position. Of course, this is the pole, this is my principal focus, and this is my center of curvature. So I'm placing this object now at before, okay, before the principal focus. So now the ray of light at the top of this object which hits this mirror, remember it will reflect, right? If it reflect, it actually passes to the principal focus. Now how do I get to form the image? Let me draw this one. Okay, okay, so of course, so how do I get to form the image? The image is formed, okay, when this reflected ray and the one passing through the C, okay, intersect. The line passing through the C, passing through C, okay, goes forward and doesn't deviate. And as you can see now, if I'm tracing what I'm tracing now, I'm tracing it behind the mirror. So the line passing through C and the line that reflected, if I should trace it behind the mirror, at the very point where they intersect, okay, if they ever intersect, definitely they will intersect. So at the point where they intersect, okay, let's say they intersect at that point, that is the point where my image will be formed. So as you can see now, with what I have there, this image, okay, the characteristics of the image is erect. So when I have my object placed between the pole and the principal focus, okay, the image that is formed, as you can see here, is erect. And of course, for the fact that this image is erect, okay, every erect image, the erect image is always virtual. Of course, you know what I mean by virtual. As you can see, I traced the rays that form the image is actually traced, okay, behind the mirror. It intersected behind the mirror, okay. So when you look at the image is not cast on the mirror, but it's actually formed behind the mirror. All right. Number 3, another thing you notice about the image is that it's magnified. That is bigger than the object. Okay, and of course it's formed behind the mirror. So that is one characteristics when you have the object being placed before F. Okay, let's look at another situation where the object now, okay, is now brought back from this point. Now bring it to F. Let's see where U is equal to F, where the object is equal to F. Let's also draw the ray diagram of that. Okay, let's draw the ray diagram of that. Now we have my principal axis. Okay, then I have excuse me, principal focus, center of curvature, the pole. Then I'm placing this here. Okay, draw the ray, parallel ray. It reaches there, then it reflects, still passes through this point, and of course if I draw a line directly, okay, of course I need to extend this. Okay, all right. So if I should trace this now, trace this, it's called that two of them are parallel line, they will not meet. So what's the nature of the image? So you now discover that when the object is placed at the principal focus, the image that is formed, at infinity. So please take note of that. Object placed at principal focus, image is formed as at infinity. So we don't know the nature of image. Why? Because the image is at infinity. All right, now the next thing I'm gonna do is that now I'm taking this object now, and I'm going beyond F. Okay, so I'm looking at where U is now greater than F. Okay, what then that happens? Let's still draw the ray diagram of that. Okay, so here we go. Okay, so I place this my F, this is my C, and here I'm placing the object at this point. This reaches, refracts, okay. Then in this case now, this one gets to the ray also this time around hits here, okay. Then also reflect, please, not reflect. So it is when these two reflected ray actually intersect at the point where they intersect. Okay, that's where I will form my image. So as you can see now, this image now is formed in front of the mirror. Okay, in front of the mirror, formed in front of the mirror. Okay, that means it's real. The image is real. And as every real image now, as you can see there, is inverted. Image is real and it's also inverted. Number 3, okay, the image is also magnified. Now if I bring it now from here to C, okay, if I bring the object at a point beyond F to the point where the object now is at C, okay? Now the characteristics of the image you will have is, of course, it is real. The image will also be inverted, but that image will not be magnified, okay? It will be the same size as object. Then another thing you should know as when you place an object at C, the image is formed at C also. So the image position will be the same as the object position formed at C. Okay. So now when you now take when we now go beyond, when the object now is now greater than, so the image now is now going further from, because as the image, as the object, please pardon me, is going further from the mirror, okay, the image will be reducing. So at this point here now, you discover that yes, the image is real, and of course, and inverted. Every image is always inverted. Okay, but there's something, okay, worth noting about that image. When you now go beyond C, the image now is less than the object, so the image is actually diminished because you are going far away from the mirror. Okay, so these are basically the characteristics of the image formed by a curved mirror. Okay, now this curved mirror now I'm using, this instance is concave mirror. All this instance now is for a concave mirror. So we're going to look at that of a convex mirror. Okay, but before then, let's now study our mirror formula, okay, or the mirror equation one more time, because we have to solve some questions. Mirror equation. Okay. All right. So now, mirror equation, I have 1 all over f equal to 1 all over u plus 1 all over v. That is when the v, okay, when v is for virtual, is for real, please pardon me, when it is real. But when you have 1 all over f, 1 all over u minus 1 all over v, it simply means that the v, okay, is virtual. Now the question is, when do I really know if the v is virtual? Okay, remember, for a concave mirror, the only time you get a virtual image is when the u, the very time the u, okay, is less than the principal, the focal length. So for you to know whether the image is virtual, okay, for you to know whether the image is virtual, if they give you a particular question for a concave mirror, quite well, check the position of the object, compare it to the focal length, then you know whether the image is virtual or real. That's another formula. That formula is a formula for magnification. Magnification of a mirror, okay, is talking about how big the image is with respect to the object, and it's given by the formula v all over u, okay. M is equal to v all over u. So that is magnification. This is a formula for magnification of the mirror. So that particular image is said to be magnified if its size is greater than the object. So now this v can be, this v, of course, you know very well, it can be either the image size, okay, or even distance from the mirror, the image distance from the mirror. Then u U is the same, is either the object size or distance. Okay, so I hope that is well understood. Let's look at some question. Okay, let's look at a question where we are told that an object an image is twice the object. In a mirror of focal length. Okay, in a curved mirror, please take note of the curved mirror of focal length. cm. What is the object and image distance? Okay, so now first of all, let's get to find the object distance solution. For me to get the object distance, of course, I'll need the formula 1 over f is equal to 1 over u, okay, then plus 1 over v. Now, I'm using plus since already I don't know any of the image and object distance, but from what I have here, I was told that the image, okay, is actually 2 times the object distance, so I can create this relationship v is equals to 2u. Okay, so in this relationship now, I can now have that, okay, 1 over f, which of course is 1 over 15, is going to be equal to 1 over u, then plus 1 over v, which of course v is 2 times the object to u. So we can go by LCM, okay. The LCM here is 2u. U divided by 2u divided by u, I have 2 times 1 is 2. Then plus 2u divided by 2u, that is 1 times 1 is 1. So all over 1 all over 15, okay. So let's do this. This 1 all over 15 is equal to 3 divided by 2u, so I can cross multiply. 2u multiplied by 1, that gives me 2u. 3 times 15, that's 45. So u now is going to be equal to 45 divided by 2. So that should give me, how many is that? 22.5. The object distance is 22.5. So if the object distance is 22.5, then of course the image distance is 2 times the object distance. That means the magnification is 2, right? So 2 times the image, 2 times 22.5, and that's 45. cm. All right, cm. So that is one question. Okay. Let me still get another question. So give me some time to get some other questions so that we will do justice to it. All right. Okay, so I have another question here. It goes this way. An object is placed 30 cm. I will only write the parameter this time around. So the question goes this way. An object is placed 30 cm. That means u is 30 cm. All right. From a concave mirror whose radius of curvature. So radius radius of curvature of this concave mirror is 30 cm according to the questions, from a concave mirror whose radius of curvature is 20 cm. Please pardon me. The radius of curvature is 20 cm. Okay. Determine the position, nature, and the magnification of the image. Determine the position. That means we are looking for the image distance. So after finding the image distance, we find the magnification. Then we'll also talk about the nature of the image. All right. So what do we do? Now remember the formula: 1 all over f is equal to 1 all over u, then plus 1 all over v. In this case, I have to test if the v is virtual or is real. How do I do that? Okay, I have to compare that. First of all, I was not given the focal length, but I have to find my focal length from this radius of curvature. Remember what I told you, that the radius of curvature is always equal to 2 times the focal length. So focal length now is going to be equal to the radius of curvature divided by 2. So this is going to be equal to 20 all over 2, which is, of course, is 10 cm. Okay, so if that being the case, now it is now very much easy for me to compare. So you discover that my focal length is 10 cm, but my object distance is 30 cm. That means object is greater than the focal length, so my image definitely will be real. So I will use the plus sign of the formula. So let's go there. So I'm going to have 1 all over f, which of course is 10, is equal to 1 all over u, which is 30, then plus 1 all over v. That's what I'm looking for. So rearranging this equation, 1 all over v now is going to be equal to 1 all over 10. Okay, so if I should collect that, then 1 all over 30 goes to the other side, because minus 1 all over 30. Okay, so of course, you know what we do, we apply simple LCM of the denominator. The LCM of the denominator is 30. 30 divided by 10, that's 3. 3 times 1 is 3. Then minus 30 divided by 30 is 1. 1 times 1 is 1. Okay, so I'm having 1 all over v is equal to 2 divided by 30. Okay, so v is going to be equal to 30 all over 2, which is 15 cm. Okay. Yep. Yeah. So now let's actually before we look at the magnifications, okay, what's the nature of this image? The image is 15 cm, and of course the object is 30 cm. So you discover that this image is diminished, less than the object. Now we can calculate the magnification. Okay, the magnification is v all over u. Image distance, which of course is 15, divided by the object distance, which is 30. So that means the magnification is 0.5. So magnification, once magnification is less than 1, it simply means that that image is actually diminished. Okay, but don't also forget the image is diminished. Okay, number 2, another nature of the image is that it's real. The image is real, it's not virtual. Okay, that is it for now. We will look at more questions in the next video. Right, see you in the next video. Thank you.